Okay, okay, so let's get started. Today, welcome to another session, to the sixth session of the Probabilistic Machine Learning Reading Group. Today, our speaker will be Daniel Corrales, who is doing his PhD at the Institute of Mathematical Sciences in Madrid. He is currently working in test time adaptation from Bayesian approaches. And he'll be talking about Bayesian neural networks today. So thank you, Danny. The floor is yours.
Okay, thank you, Pablo. You can hear me all right? Yep.
Yep.
Okay, wonderful. Okay, so thanks for the presentation, Pablo. Indeed, I'm going to talk today about Bayesian neural networks. I'm sure everyone has heard about neural networks, but maybe not that much about that first part. But as we're working, like this reading group is on probabilistic machine learning, I think that that first part is crucial, and that's what we're going to try to understand today. So, um, just an overview of the contents. I'll first introduce what predictive models are in general, and then try to motivate the usage of Bayesian methods for predictive models, and then extend it to neural networks in order to cover a larger set of models, more flexible, more complex. We'll see. Uh, as always in Bayesian methods, we'll have to make decisions about the predictive posterior, how to calculate the predictive posterior, the prior, and then how to do inferencing for the posterior distribution, because it's going to be a hard problem and intractable. So we'll have to make approximations there. I'll introduce one use case, very brief, on online learning, and then I'll try to extend a bit more on generalization power of Bayesian deep learning. So, what are predictive models? Well, in general, we're in a setup in which we want to learn how to predict some outputs. We have some data or some inputs which are X, and we want to predict this output Y using some kind of function that relates X to Y. So in general, what we have is a collection of data. In supervised learning, we have a collection of data in which we have both the inputs and the outputs for a few cases, and then we want to infer this function f based on the data that we have observed. So one way of modeling this and together model uncertainty is to say that we have a conditional probability model that outputs the y's based on the function of x. So there are, for predictive models, there are a few cases: parametric versus no parametric, deterministic versus Bayesian. We're going to be here. We're going to do parametric predictive models, and we'll try to be as close as possible to the Bayesian setting. So I'll first try to introduce how learning is done for the deterministic case, and then compare to the Bayesian case. So an intuitive way of thinking about this is we want to find the best parameter that defines the relationship between the inputs and the outputs. No, and how do we measure that best parameter? We say, well, it minimizes some kind of loss that measures the goodness of fit of the data and of the data on the input and output. So that could be basically it. Find the best parameter theta that minimizes a loss. However, we usually need some kind of regularization, because if we have a finite data set, we can, and a very flexible model, we can get to the point that the model can basically memorize the data and have a perfect fit on the data we have. In general, this could be of interest, but in general, what we're doing is we're inferring a model in order to use it later for more general applications. And in other applications, the data is going to be similar, but it's not going to be exactly the same. So there's no point on exactly memorizing the data. I think we all can understand this. So this loss function can be a measure of goodness of fit. For example, the log loss, which is the log of the likelihood function, and then this C of theta is a regularizing factor, and then there's a lambda parameter that measures how much you're regularizing, how much you're fitting on the loss. So one of the cases, sorry, yeah, a specific case of this deterministic, and it's a midpoint between deterministic and Bayesian learning, would be defining the regularization factor as the log of a prior distribution P0, and then also use lambda 1, and we recover the maximum a posteriori estimate. Hold on to that because we're going to see it later. So in a Bayesian setting, instead of finding the best parameter, of course that's going to be always a parameter of interest. However, there might be more parameters that also have good properties, and one of the motivations of doing using Bayesian methods is that we can average over a distribution of the parameters. So in this distribution, we are considering the parameter that minimizes this loss, but we're also considering a whole range of parameters, a whole distribution of parameters that can help us predict better and have better uncertainty estimates about the predictions. So the thing is, here we're gonna have to integrate. So this we're gonna have to integrate over the whole space of the whole distribution of parameters. That makes it a bit harder, but in a way marginalizes the whole problem in order to consider all the parameters, and each of them with a certain weight. So what's the probability that we get data Y based on that we have an instance of theta and the probability that theta comes from the data. So if the probability is low, then this average is going to be low. If the probability is high, this term in the average is going to be high. So we average over different possible models and weight them, and then we calculate this posterior based on the likelihood, which is what we had earlier. We talked about minimizing some loss, and then also prior distribution. Here we can see just like a very common example of how to understand Bayesian inference. We have a prior distribution, a likelihood, and then the posterior is some sort of average between the two. And then, as I said before, the map estimate is going to be the highest point here at the distribution. No? So like it's usually going to be that. Okay, so what are the motivations mainly? As I said, we want to define a distribution over the parameters that lets us represent uncertainty more accurately, and we are considering a whole set of models instead of only just one. So that can lead to improve accuracy and uncertainty estimation. However, but for a few model or linear cases, linear Gaussian cases, or some closed form solutions regarding conjugate models, in general, integration here, integration usually here as well, has no closed form. So we are going to require approximation methods in order to calculate all these quantities. So the problem is intractable, and the rest of the talk, and usually this happens when using Bayesian methods, is that we're going to need to find how to approximate these distributions and this every element in here. So we're going to need a prior, which is going to reflect our beliefs about the parameters before seeing the data. And we have to specify that based on our beliefs. before seeing the data, as I said, it's which is not a simple task, and we'll go over that topic during the talk. And then we also have a likelihood, which represents how well the data supports a specific hypothesis. So how well this data, based on having a specific instance of theta, how does theta represent this data? Then we're going to combine the two for posterior inference, because we, as I said, for doing Bayesian model averaging or for marginalizing over the weights, we're going to need some approximation, at least, of this expression of the probability of each of the weights given the data. Also, there's another element that is important for Bayesian inference, which is the evidence, which is the total probability of the data under all possible hypotheses. And then finally, in order to do prediction, we're going to marginalize over the parameters to predict and have this predictive distribution. So these are mainly the main ingredients for doing Bayesian inference. In the simple settings or more classical settings, but also they're going to be translated to more complex settings, such as Bayesian neural networks. So just to give a brief example of how Bayesian modeling works, where I'm going to define a classic linear regression problem. Here we assume that we know the sigma, and here's the linear relationship between the input and the parameters in order to get some output y. So we assume that the noise is Gaussian. So this is the observation model with a Gaussian noise, and the likelihood of that observation model is assuming that the observations are IID. It's a product of normal distributions, of Gaussian distributions, with mean this factor of the linear regression, and then variance the sigma squared. So we have to set a prior. As always, we'll decide on how to set this sigma 0, and that's going to influence then in the posteriors, as we shall see. So in this case, everything is normal, everything is Gaussian. So we have a closed form solution for this, in which the posterior can also be represented as a Gaussian distribution with a certain mean and certain variance that is obtained from the data, and this sigma that we assume it's known, and the prior. And then the predictive posterior is also going to be Gaussian. So this is very clean. This is ideal. However, the main limiting factor is that the relationship between the data and the parameters is linear, and that's going to be a bit too simple. So, but just to get an intuition about this. So first, more graphical intuition. We have a prior over the parameters, which is Gaussian between -1 and 1. We can sample from this distribution, and we get a whole set of lines that actually don't have much meaning. But as we start to get some data, this prior contracts based on the data. This contracts to a distribution of the parameter beta 0 and beta 1, and we have a better estimation of what the value of beta 1 is and beta 0 and beta 1 is with more certainty. And this is as we are adding data. We can see that in the data space, the possible functions that appear, as we have learned, are more aligned with the relationship that the data actually has, way more aligned, of course, than in the prior setting. Okay. So what if we need more complex modeling? So, of course, linear regression, it's a very useful tool, and it's been used for forever, and it's still going to be used because it still has a lot of properties that we need to deepen on. However, a first idea that comes to your mind is, what if we make this more complex. So in general, deep neural networks, we've seen in the last few years that they've been working very well. So an idea is how to leverage deep neural networks for modeling this uh, conditional distribution. So we define a very complex relationship, or much more complex relationship between the x and the theta, with the goal or the aim that we can learn better and from more complex distributions and all that. So as I said, deep neural networks, I think we all have an image in our head of how they are and how they work. They're very large flexible models. They can represent many functions. However, anyone that has worked with neural networks can say this well. They can converge into they can fit the training data very well, but they can converge to very different parameter settings. No, so like sometimes you need to, like when you're implementing them, you have to fix the seed. So that the same solution always comes out as you redo the experiment. And this is because the model is underspecified. So there are a huge bunch of combinations of parameters that actually output the same predicted distribution. So the model is underspecified, and also there's a lack of identifiability because it's not like we're going to have a single set of parameters that is always going to do to predict the same y based on x, but we can have a huge bunch of them. So how can we leverage this? Well, we can benefit from this using Bayesian model averaging, because on this fit in the training data, it's like not all combinations of parameters are going to generalize that well. So they can fit the data in the same way. However, not all of them are going to be as useful in terms of using them for another task. So what we think is why don't we benefit from Bayesian model averaging and then marginalize over all the possible combinations of weights, so that we have a better estimation, maybe more realistic, or who knows, like a better estimation of the predictions. So instead of just using one, using a whole distribution of parameters. So that's the idea. However, this has some pros and cons. Well, this maybe it's a more graphical idea. In a standard neural network, you have its weight, its relationship between the x, the biases, and the hidden network are characterized by using just a single parameter. Here, we're going to average over a whole distribution. Of course, there's going to be a mode, so they're going to have certain peaks, but the information is going to come for the whole distribution. So of course, Bayesian neural networks inherit the ingredients for Bayesian inference. So in Bayesian neural networks, we still have to define the prior distribution. We have to define the likelihood distribution, the posterior, and the predictive posterior. So we have a huge benefit, which is that our model becomes more general. It can basically fit a huge bunch of data sets and models. However, this comes at a cost, and is that as we have increased complexity, we're losing convexity, and thus we're not always going to reach the same minimum when optimizing, and the loss is gonna look terrible, and we're also compromising inference because the dimensionality is huge. So these integrals here are going to be very, very hard to compute, and we're going to have to rely on approximate methods. So I'll try to go briefly over the predicted posterior, prior distribution, and the posterior distribution. I don't know if there's any question already, just of the idea of Bayesian neural networks. If not, I'll continue. Okay. So, as I said, we need to characterize the basic ingredients for Bayesian methods, also in this um, field of Bayesian neural networks. So I'll go into the predictive posterior distribution, how to characterize this, how to characterize the prior distribution, and the posterior distribution. So for the predictive posterior, which it'd be the last step of the pipeline, but I'm going to assume a very simple approximation. This integral is in general very hard to compute because we're not gonna have this in closed form, and we're not gonna have conjugacy here. So what we usually do is we do Monte Carlo approximation. So we sample from this distribution, we get a few samples of this, and then just average all this, the likelihood with these instances of the parameters, average those, and then get an approximation of the predictive posterior. There are better ways to do this, but this is the most basic one, and it's usually the most used. However, this has a problem, which is that this distribution, this posterior distribution, will also be approximated. So we're approximating, sorry, in two steps. We're approximating here when doing Monte Carlo, and we'll also be approximating when estimating the posterior. Next, the prior distribution. So in general, prior distributions are set so that they reflect our beliefs on the problem, and it's sometimes they might be not thought about much because they seem to be not important. But however, the priors are actually quite important because they define the range of functions that are actually going to be representable by the model. So they give some probability higher or lower to the type of function that might appear in the model. So and a very intuitive way of defining the priors is just saying, okay, I'll just have some priors for MLP, which is a normal standard neural network, which have some weights and biases. Each of the weights are just going to be initialized using some Gaussian, and also the biases are going to be initialized like this. The choice they're going to depend on a choice for the covariance, well, a covariance factor here. And then depending on the choice of this, we're going to have some type of functions or others. So this is a very naive example with a two-layer neural network, but already shows that the choice of these alphas and betas actually influence greatly the function that come up at the beginning with the prior knowledge that we have. The thing is that in general, in Bayesian neural networks or in neural networks in general, we translating the idea of I want this type of function or this other, and relating that to the choice of weights. It's not straightforward, but this already shows that, for example, for alpha 2, which would be the alpha 2 here for the weight, so the outest layer. Increasing that will have quite a big increase in the amplitude of these functions. However, increasing the bias also has an increase or horizontally. So ideally, we would have to think, okay, we have some prior knowledge about how the functions how I want the functions to be. So if I want them to be more flat or more peaked, however, when using huge neural networks, this intuition actually is a bit lost. So a second way of doing this would be to work on priors on function space. So instead of modeling the priors on weights, we would think of actually directly modeling the priors in function space. So what kind of functions do I want? This is a growing topic in the field, and the attempt usually looks for designing more informative priors. So, for example, we want certain invariances because we know that our data has certain properties, or locality, or independencies, or symmetries. We know our data has certain properties, and it'd be too naive to just input any neural network with any prior initialization if we already know that our data behaves in a certain way. So this tries to leverage this, and it's done in a similar way to parameter initialization, but here I think the intuition is more direct because you're already defining from the beginning. You're defining the functional priors. And then also a very important topic would be architectural priors. So the design of your neural network is also going to be important in with regard to the data that you're analyzing and the output you want to obtain. So, for example, some neural networks have a very large effect on induced distributions over functions. So this is called inductive bias. Why do we not use standard neural networks and use convolutional neural networks to analyze images? This is because convolutional neural networks, they already encode some prior knowledge about translation using convolution. So this is going to be very useful when analyzing images. So already the architecture, designing the network already induces a type of function that is going to represent our data. So it's also important to give a thought to this, and this is a field that is called neural architecture search. So these are mainly a few sets of options for the priors. We'll go over that in the last part on generalization. Now I'm going to briefly explain some inference approximation methods for the posterior distribution. So as I said, a quite standard way of doing Bayesian inference, well, not of doing Bayesian inference, but like approximating Bayesian inference through point estimates would be using the maximum a posteriori estimate, which was the parameter that minimized that regularized loss functions between the likelihood and the prior. However, as we said, we want to define a whole distribution over the parameters. So we can write our posterior as the exponential of this energy function, which is going to be the probability of theta and d, and then performing a second order Taylor expansion around the mode. We can approximate this whole function by this term in the right hand side, where g is the gradient and h is the Hessian evaluated at the mode, and then this results in a posterior distribution, which can actually be interpreted approximated as a Gaussian distribution. So here the idea is that we are approximating this function locally, because we're using a Taylor expansion, but locally and around the mode. The mode is going to be the maximum posteriori estimate. Around the mode, this we can approximate the posterior distribution with a Gaussian, which covariance is going to be the inverse of the Hessian. So that's going to measure the curvature of the loss at that point, at the point of the map. So this is a very simple approximation because we're using the map estimate and then fitting a normal distribution around it. And the thing is that it's the map is obtained through optimization, which that's quite handy. And then we can obtain, as this has been obtained from optimization, then we can approximate we can get a Bayesian estimate for any pre-trained model just by using this and the Hessian on that point. So that's a good thing, but it's also a bad thing because then the curvature information um, is only used after the model has been estimated and not during the optimization problem. So process. So of course we're losing some information and we're only approximating the model with a normal at the last step. So when the model has been already optimized in a way. And also another factor is that computing the Hessian, it's very expensive. However, some method exists. And a main drawback of this method is that it's very highly local. It's unimodal. We're only using the map estimate to fit a Gaussian around it. However, it has some good things as well. So this is originally the one of the first approximation methods that come up in the Bayesian neural network literature by Mackay. So if you want to read about it, it's quite interesting. A next step could be to consider variational inference. It's also one of the next steps that researchers came up with for doing inference in Bayesian neural networks. And the idea of this is to approximate uh, the posterior distribution with a distribution of choice. So this has already been explained by Pablo in the second lecture of this reading group, but basically we choose a distribution so that minimizes some kind of distance between the true probability distribution, the true posterior, and the distribution of choice. And then the key thing here is to define this size, which we usually do using a Gaussian approximation. This is interesting because instead of using the posterior, this can be rewritten and not consider the normalization factor, which is usually the most the intractable part, and you're turning a marginalization problem into a optimization problem, so minimizing a KL divergence. So the idea is sort of like this. So you're trying to fit this kind of model, for example, with a Gaussian for a real true posterior, which is this, can be also understood as being the closest as possible to the target distribution within your space of possible distribution. So the good thing about this is that it's done doing gradient descent, and optimization is quite fast and easier done when doing so like optimization is easier than integrating. Usually, well, Gaussian approximations, they underestimate the uncertainty, so other models can be used, such as normalizing flows or implicit distribution. They partly mitigate these underestimations. So some properties about variational inference. In general, it's a simple method. It's optimization based, and the curvature is analyzed at every step of the gradient descent. That is very nice. However, it can also lead to local models and unimodal and have and be a bit overconfident when the actual posterior is not unimodal. However, anyhow, it's one of the methods that is most commonly used when approximating Bayesian neural networks. MCMC methods, they also appear around the same year. So this is the 19th in order to solve Bayesian neural network. There's a very nice talk given by Miguel and another one by Mario on this. That's the third and the fourth of this reading group. This is so that you get an idea of why we talk that much about inference methods, because when you translate them to modeling, they're used, and that's the way we solve this model. So it's not only about having a strong neural network that works, but you also need to understand how inference is done there. So Hamiltonian Monte Carlo is considered the gold standard, but well, because it doesn't make assumption about the form of the posterior. We've seen that in variational inference and Laplace approximations, we're assuming that the posterior has the form of a Gaussian. Hamiltonian Monte Carlo doesn't make this assumption. However, in general, this as we could see in earlier sessions, these methods are very costly, and well, people have came out with more scalable alternatives such as stochastic gradient with Langevin dynamics, which they can operate using mini batches, but still they're quite computationally intensive. However, they have this benefit that they don't make very strong assumptions about the posterior. So these are perhaps these were the most Bayesian well-founded methods. However, new methods have also come out in the literature, and I'm going to briefly explain on this. They're not far from being Bayesian, just the construction is a bit more heuristic. So, for example, this the HGD trajectory-based method. So HGD is the stochastic gradient descent, and basically some work on Ismailov and Andrew Gordon Wilson. They noted that stochastic gradient descent solutions, they surround the periphery of good points with points with good generalization. So they propose to average the samples of HGD and then collect them and average so that they get a better approximation. So this can be seen in this image. So if we have a stochastic gradient descent that with a fixed learning rate that starts bouncing against these walls, this might be approximately that there's a good point with good generalization here at the center. So the idea, which is well, it's a bit heuristic because it could not happen like this, but they show in their papers that it's actually the case many times. So it has perhaps a worse loss for training, but a much better loss for test than over optimizing the model. So in a way, it can also be understood as a form of regularization. So what they do is on those points that I showed, they fit a Gaussian distribution, and they approximate the posterior using a Gaussian, but at those points. And they further use multi-swag, which in which they can detect different modes, so not only one, and then approximate the posterior through a mixture of Gaussians. So this is very interesting because, as I said, it's used. They use HGD solutions, so they're optimizing the problem as a standard neural network, and then they're defining, they're collecting an average, and then they're defining a posterior around this mode. So it doesn't take much longer to compute than standard training, and it leads allegedly leads to better generalization, and it improves accuracy and calibration. So it's actually a very interesting paper. I would really recommend to have a look at. And then perhaps the best performing models that have decent uncertainty estimates, but are also some kind of approximation to Bayesian inference are deep ensembles. So in deep ensembles, the idea is to have a standard neural network and train it a few times with different initializations. As I said earlier, these different initializations can lead to different optimal parameters, and then you approximate the posterior using a weighted mixture of delta functions at those optimal parameters. So you train a few, say you train M models, you get the map estimate, so the optimal parameter for that, and then you average all of them. This could be seen as a M version model M version of the map estimate. So like map estimate, we only approximate the posterior with one element, and in here we're approximating it with M. And it's been argued that deep ensembles can actually be a good approximate for the Bayesian posterior predictive, so they are considered also Bayesian. The key factor here is how you define different initializations, so you actually converge to different map estimates that are actually in different basins of the loss function, so that you actually have a whole range of good estimates over which you can average. So the good properties about this is highly multimodal. So we could see the image here is quite small. Oh, maybe I can do this. Yep. The image here is quite small, but basically deep ensembles find a few modes and then average over that. They allegedly have a better generalization power. This is the validation loss, and all these are multimodal. However, variational methods are unimodal, and then they approximate one of the peaks, and they approximate it very well. However, what it says that for generalization to be better, it's more interesting to find several different modes than actually having a distribution around this, an approximate distribution unimodal for approximating this. I'll show you a picture now. The bad thing about deep ensembles is the high training cost. We're basically doing standard training n times. That of course is a huge burden. So this is a table comparing all the methods, but I'm a bit tight on time, so I'll rather go to some examples. So this is an example of a regression problem approximated using deep ensembles, SWAC, Laplace, BI, and MCMC. We can see how the execution time of ensembles is quite high for this case. And then, for example, the performance of BI using mean field approximations is quite low, but the rest of the inference methods actually approximate the data quite well and in distribution, so where the data are, but also outside the distribution, they approximate the true function relatively well. Not that well for SWAC in this case. Also for another comparison of Bayesian neural networks with like several inference methods, we have here for a classification problem of the two moons, how each of the inference methods would perform. So in terms of execution time, the highest one is MCMC. However, we consider this the gold standard. We see that it approximates really well uncertainty between the classes, and then outside of the distribution, it has a very high uncertainty. In terms of expected calibration error or Beer score, the lower the better. So we see that HMC, Hamiltonian Monte Carlo, or ensembles are usually the best models in terms of performance. However, in terms of analyzing the uncertainty out of the distribution, we see that these models are quite overconfident that the data distribution is going to have this shape. Ideally, we want more uncertainty like this. We want more uncertainty outside the distribution because we don't have information in those areas. We want more uncertainty there. I don't know if there are any questions about this, or I'll continue with generalization.
I have one quick one. In the first part, when talking about the posterior predictive distribution, we usually do it with MC samples, as you said.
Yep.
But you said there are better ways of doing it, such as?
Not like there are better ways, but there are alternatives. So, for example, if you approximate your distribution using a Laplace approximation, it can be better to do some kind of linearization of the distribution there, instead of just sampling, understand it as a different distribution, linearized, and there are better ways to do that. There's some, I think there's some options in the book, and if not, I can also send you some reference on that. It's not like it's super common, but it's not direct. That way is the optimal.
Okay, thanks.
Okay, I'll continue then. So I had a brief slides on online inference. I'll just explain the motivation and go to a generalization because I think it's quite interesting. So Bayesian inference in general can be used for online inference, and it's a natural framework because you're basically updating your beliefs, and today's posterior becomes tomorrow's prior. However, this is not that direct in general because maybe today's data is not as good as yesterday's data, so you want to not forget what you learn, and not overfit on the things that you're learning now or today. So usually we use reweighting factors for this, but as I said, it's quite a natural framework to work on. You have some updates of your theta based on the data, but then also you have some kind of transition between today and yesterday, and today and tomorrow. But anyway, I much rather talk about generalization in Bayesian deep learning, because I think it's a very important part of this, and I think it's where most of the new things of the new things are being studied. So I think I want to at least like set a seed in your head to like think, well, why generalization is important, and how Bayesian deep learning might benefit or have a good response to generalization. So the key is that we're marginalizing rather than using a single set of weights. However, that's not enough to guarantee generalization, because this the whole distribution of weights can be very similar all to each other, or can result in very similar predictions. So that itself doesn't actually guarantee good generalization. It also depends on support of the distribution and the inductive bias of the distributions that come out, or the type of functions that come out from the Bayesian neural networks. So also another difference between classical and Bayesian, well, the main difference between classical and Bayesian approach is that it depends on how sharp the posterior is. So if we're very sure about our data, they're going to be very, very similar. However, if we're very sure about the distribution of our weights. However, in underspecified models, which are Bayesian neural networks always, likelihoods are often more diffuse, and they don't favor any one set of parameters, so we can average them all to get better results. So the idea is that we want a big support. Okay, so that we want models with a big support that can represent a large set of functions. However, we also need some inductive bias. So like, we do not want a model that can represent any function with the same any type of function or any type of data set with the same probability. We want to favor certain kinds of data sets. So for example, in the case of classifying images, a very complex model would be, well, a very simple model would be approximating classifying images with a linear function. However, the support is very small. It's like it's not going to do that well. So another option would be to use a normal neural network, a multi-layer perceptron, which are, in general, they can be understood as universal approximators. So they have a very large support. However, they don't have these inductive biases that actually benefit from the type of data that is used. So in this little example, the best specified model, a well-specified model, would be a convolution neural networks, because they favor some kind of properties in the images, and they can benefit from this. So we want uh, this inductive bias to represent the relative prior probabilities of all the hypotheses that are made. So it's not like we're only looking for flexibility of a model, but also from the complexity of a model class. It's something that we have to both leverage and trade off. Also, as I was saying earlier, most Bayesian deep learning methods focus on approximating a posterior within a single basin of attraction. So, for example, using the map or fitting a Gaussian over fitting a Gaussian, which is in general unimodal. So, arguably representing multiple basins of attractions in the posterior can lead to better generalizations. This is an image of a work on deep ensembles and multi-swag, and the idea is that if this is your best approximation for VI, for example, which are the orange dots, this is going to be a good approximation for this part. However, the difference in the predictive function is it's not going to be much. So you're averaging over a set of predictions which are not too varied, not too different from each other. However, if you actively detect several important modes, you can get a better estimation of the possible predictions or possible values of the predictive for the Y, and then averaging all these four, for example, would have a better estimation of the actual probability of the probability of the class Y or the label Y. So instead of doing just unimodal approximation, trying to leverage multimodality, the multi-basin models, multi-basin in the loss, that gives better generalization. Also, there has been a lot of work on flat losses in terms of we rather have a flat minimum than a sharp minimum. And this is something that stochastic the SWAG models actually benefit from. They argue, well, this is a very simplified diagram. They argue that in around flat minimums, the difference between training and generalization loss is not that high. So the generalization gap is small, while around sharp minimum, of course, we're training using a finite set of samples. So of course the generalization law is going to be different because of this finite set, which is going to lead us going to be noisy. So we expect generalization loss to be a bit different than the training loss. So they argue that in flat minimum this has a less of a big impact than in sharp minimum. This can be seen in this image. And just to finish, some limitations of Bayesian neural networks. So in classification tasks mainly, it has been proved that instead of writing the Bayesian posterior in a standard way, if you use this power, this temperature, the accuracy gets better. So it's argued that tempering, which is called tempering the posterior distribution helps under model misspecification, which is always going to be the case using neural networks. They're huge models and they're not going to be well specified to the data. So the thing is that using these temper posteriors is actually a problem because it's not the standard way of thinking in Bayesian in a Bayesian way. So this can be seen in a few articles. This is a picture of one of them. So the accuracy is higher as the temperature is lower than 1, and this would be the strict Bayesian case. And we see that the accuracy lowers down from 93 to 88, which is quite a big step. So why is this? Well, mainly the main argument is that the model is misspecified, and also that we're underrepresenting aleatoric uncertainty. So for the first part, if the model is misspecified, then something is probably wrong. Inference methods are shown to be quite well defined, and all the attention is now going recently is not going to prior misspecification. So we're not defining the priors right. So the possible functions that come out are not they don't act accordingly to what we want. So we have to temper the likelihood. But also, some recent work argues that the goal posterior is due to using softmax likelihood. So in regression, we have some uncertainty always about our observation function. However, in classification, we do not have this parameter that measures uncertainty. We just do a softmax over the neural network, and then this avoids us to having a good estimation of the aleatoric uncertainty. So that's going to be it. It's already time. Some final remarks so that we can think about Bayesian neural networks in a big framework. So they are beneficial for increasing accuracy and uncertainty. The main tasks to do are to specify the prior and approximate inference, and then future steps in Bayesian neural networks are mainly in the direction of studying model generalization and then representing aleatoric uncertainty and prior design. I'll finish with a slide of the missing topics. Of course, it's a very broad talk, and I almost ran out of time. So I haven't talked about last layer methods or partially stochastic networks, other alternatives to Monte Carlo approximation, as Pablo asked, to the predictive posterior, functional Bayesian neural networks, which seem to be quite active now, and a very important part in general in Bayesian methods, which is model selection and marginal likelihood. I encourage every one of you to read the book and read a bit more on all these topics. So thank you. Do you have any questions?
I do have a question. Thank you for the talk. It was lovely. I wanted to ask a question about the slide where you explained how when you get a parameter from a point in the procedure which is flat, then those models tend to generalize better. And I was wondering if you had any intuition as to why that seems to be the case, or if there are like theoretical results which show this.
Well, in general, I would say the results are more heuristic than theoretical, but there's a lot of work on this. I can also share some references. The idea, I think this diagram actually represents the idea very well. So the training loss is subject to your limited data that you have for training a model. However, when you're going to use that model, the distribution is most likely to be a bit different. So if you had to train that model on the new distribution, that loss would be a bit different than the loss used during training. So in flat regions, that difference is not seen that much. So this is the generalization loss. This would be a training loss. That difference is not that it doesn't affect that much. While in sharp minimum, it would really affect this much. So like if we get this minimum and optimize over this in the generalization loss, it would be this point over here, while for the flat minimum it'd be here. I think the intuition is interesting, but in general, the works on this are more heuristic than theoretical.
Okay, thank you.
Okay, thank you, Sergio.
I have one other question. It's regarding the priors on the architecture. How do you include that prior of what model to use into a prior? Because most examples of priors are normal Gaussians. How do
Yeah.
you include that information?
Well, the idea of that slide is that it's not something that you're including in the calculation of the Bayesian posterior, but it's something that like defining a model is going to affect how your so defining a model is going to affect how the possible posterior functions actually are, like their characteristics. So it's not like something that you define in the prior or in the likelihood or the posterior. Is something that, as you're approximating the likelihood using a neural network, this architecture of the neural network is going to affect the possible function that might be representable. So that's how you set it. It's not like you set the prior. Like you could do like you can combine architectural priors with Gaussian priors. So like Gaussians are for the weights. These are for the model that you're using.
Okay, thank you.
I have another one. You've discussed the misspecification problem that there is in Bayesian neural networks, well, and in neural networks in general. How could over-parameterization play a role into this? Because like I've seen some recent papers showing how it works with neural networks, with the frequentist ones, with double descent and all that, when they become a perfect interpolator and so on. How, like, would this be a desirable property in BNNs? How would it play a role at all?
I'm not super sure about how to answer the question. I did read these few days when preparing the presentation. I did read some work on double descent and how lowering that aleatoric uncertainty for classification model avoids or actually so like get rid of that double descent property of some algorithms. So I think it's something that it's very important to study. So I think tempering and so like correctly representing the aleatoric uncertainty. So instead of using a softmax, using a better approximation to the observation model can reduce those kind of things that happen for for the double descent that you said, for example.
Okay.
So there
thanks.
are methods for dealing with misspecification or under specification of neural networks. But I would say they do translate from Bayesian neural networks to, like, from normal neural networks to Bayesian neural networks. They translate equally. So they're the same problems or very similar problems.
Oh, okay. Thank you. Okay, I don't know if there's any other question. If not, we can conclude the talk by thanking Danny again. Thank you so much for this really interesting talk. And with that, I think we can conclude. The next session will be given by Carlos García Meiside. He's also from the Institute of Mathematical Sciences, and he'll be talking about what happens when we go beyond the IID assumption, when we are working with no IID data. And that will be on February 4th. Thank you so much.